do this. Okay, minimum cost walk in weighted graph. Hard this time. Let's see if I can solve this within a reasonable time frame. There's an undirected weighted graph with n vertices labeled 0 to n minus 1. Okay. You're given a integer n and array edges where edges of I is uv w. In case there's an edge between vertices uv, the weight of w. Okay. A walk on the graph is a sequence of vertices and edges. Okay. The walk starts and ends with a vertex, and each edge connects the vertex that comes before it and the vertex that comes after it. Okay. It's important to note that the walk may visit the same edge or vertex more than once. Okay, so there might be loops or cycles. The cost of a walk starting at node U and ending at node V is defined as the bitwise AND of the weights of the edges traversed during the walk. Okay. In other words, if the sequence of edge weights encountered during the walk is W0, W1, W2, those are the weights, then the cost is calculated as the bitwise AND of them. Okay. Where AND is the bitwise operator. You are also given a 2D array query where query at I is equal to S at I is equal to S and T, comma T. For each query, you need to find the minimum cost of the walk starting at vertex S and ending at vertex T. If there is this no such walk, the answer is -1. Return answer array where answer of I is the minimum walk cost of the walk of query at I. Alright, so a bunch of queries between some starting node and some ending node, or some starting vertex and some ending vertex. And for each query, you're trying to find the minimum bitwise AND of the weights between them. Okay, so weights of 0, 1, 7. So from 0 to 3, it's just 7, right? Wait, from 0 to 3. To achieve the cost of 1, the minimum cost of query I. To achieve the cost of 1 in the first query, we need to move from 0 to 1 with the weight is 7, from 1 to 2, the weight is 1, and from 1 to 3, 0 to 1, 1 to 2, and 2 to 1. Cost of the walk starting at node U and ending at node V. What's going on here? To achieve the cost of 1 in the first query, we need to move from the following edges 0 to 1, 1 to 2, which is 1, 2 to 1, which is another 1, and 1 to 3. And the second one, oh, bitwise AND. Okay, so I guess because if you have a 7, bitwise, that's going to be 1, 0, 4, 4, 2, 1. 4, 2, 1. And if you have 1, that's going to be 0, 0, 1. And if you do bitwise AND with a bunch of 7 and 1s, it's going to be just 1 because the zeros here would cancel these zeros. Okay. Hope that made sense. So if you did 7117 as your walk weights, it'd be 111, 001, 001, 111. If you did it bitwise and all those, that's going to be 001. Okay. And then obviously 3 can't get to 4, so it's -1 there. Interesting. Okay. So how to do this? The first simplest thing is just to determine which queries are just not possible. So you can do, okay, so for graphs, you pretty much always start with creating a mapping for input to output. So let's go ahead and create the graph mapping. So give me a default dictionary of integer. Sorry, default dictionary. Yeah. So for every edge in edges of the graph, well, it's undirected. Okay, so graph at do I need to care about this? Okay, so let's say it's u, v, w in edges. Graph at u is equal to it's a default. It's not going to be default dictionary. It's going to be a tuple. All right, it's just going to be a dictionary. So graph at u is equal to vw, and graph at v is going to equal uw. So that just lets us have a direct way of accessing from any. Oh, okay, yeah, this needs to be a default dictionary of the list. What am I thinking? Okay, so because each node can have multiple neighbors, you're going to add each neighbor to the list within that mapping. So graph at u is equal to graph at u append a tuple that is vw, and graph at v dot append a tuple that is uw. And then I'll just print the graph to make sure everything's correct for that. I don't think I need to return anything here. Alright, so from node 0 you can get to 1 with a weight of 7. From node 1 you can get to node 0 with a weight of 7, and 3 with a weight of 7 as well. Is that correct? Yeah. And then also you can get to node 2 with a weight of 1. From node 3 you can get to node 1 with a weight of 7, and node 1 with a weight of 1. Wait, so what's that last one? Node 2. Right? From node 3 you can get to node 1 with a weight of 7, and from node 2 you can get to node 1 with a weight of 1. Okay. So that's the way to quickly figure out where things go rather than using edges. Okay, so next is I'll just do the simple case where if the query is not possible, then I'm just going to have an answer that is -1 for that query. So I'll have an answer array, and then for each how should I do this? How should I do this? How fast is this probably going to be? It's 10 to the 5th, so there's 10,000 possible nodes. Okay. Okay. So for just answering quickly whether or not it's possible, generally you have like a set of values that is connected to any particular node. And then you expand that set once you traverse everything. So what if we did something like for every, so we'll have a scene set. So for each node in our graph, what we're going to do is we're going to say that if node has already been seen, then we just need to skip this. Otherwise, we're going to have seen this node. And I think so if we haven't seen the node, then this is kind of a new island of nodes that we're going to try to connect. So let's say we'll have an island set, and we'll have a traversal of the island. So we'll start with a stack, I want to say, where the stack starts with this node. And while there is a stack, what we're going to do is we're going to take the top of the stack and then connect the neighbors. I wonder if this is very efficient. This might not be very efficient. Might not be too inefficient. Alright. I'm pretty sure there's a better way than what I'm currently doing for this, but this makes sense to me. We'll have a graph for the islands, an island graph. And this is going to be a dictionary. Okay, so for each node in the stack, we're going to say n is, I already used node as a variable here. Let's say k is equal to the top of the stack, so stack.pop. And let's go ahead and look through the neighbors of this island. So then this node should be inside the island already. So the set including this node. So for each neighbor of k, and I generally I abbreviate neighbor with nay. For each neighbor in the graph of k, but here the graph at k is actually a tuple, so for each neighbor and neighbor cost in the graph of k, we're going to contribute that to the island. So if neighbor is in the island already, then just go without. Otherwise, the island will add that neighbor, and I think we need to add the island to the stack. Stack dot append the island. And each time we do k, we need to say that this graph is for k. So island graph k is equal to this current set. So this is going to be the island. Okay, so for each node that we have, that we start with, so while there is a stack, we take off the top of the stack, or bottom of the stack, whatever. We say that the current set, the current island is going to be for the k, and then for every neighbor of this node, if it's already in the island, then don't worry about it. Otherwise, we're going to say that we're going to add the island, add the neighbor to island, and then we're going to add that island to add that neighbor to the stuff that we need to worry about. Okay. I think I'm going to go ahead and check that this works as I expect it to. So I'm going to print the island graph. So for each node in this island graph, it should print out the set of all connected nodes for that particular node. So okay, so node 0 is connected to an island of 0, 1, 2, 3. Node 1 is connected to same. They're all connected in the first one, right? No, that's not right. And then node 3. I see. Yeah. So node 0 is connected to node 0, 1, 2, and 3. Because those are the actual, so there's a node 0, a node 1, a node 2, and node 3. And node 4 is actually not within the graph file because it's not connected to anything. So by default, it's going to be not in the island graph. Okay, so if a query ever goes to a node that's not in the island graph, then you know that's not possible. And then for the second case, they're all connected. Okay, so for each query, where the query is a starting and ending value, q start, I'll just say start and end node or tuple in the query. Then if either the start not in the island graph or the end is not in the island graph, then the answer is just going to be -1 for this. So if not, if either node is a complete island unconnected, then not possible. And continue. Now the other thing is they are connected stuff, but that stuff isn't linked, like they're in separate islands. But there are islands for them. So we know that if it doesn't like skip based on this, then there is start and end in the island graphs. So if island graph of start, if the end is not in the island graph of the start, then also say that this query is going to be -1. Continue. All right. Okay, so at this, actually, let's just do a quick check. Answer dot append, let's say 0 for the time being. Return answer. So this should work to identify that some queries are just not possible. So yeah, -1 is not possible between 3 and 4. All right, so I mean, this is probably a little inefficient, I think, but it is pretty sensible. Okay, so at this point, we just need to actually worry about the main thing, which is queries that are possible. So there is a connection between the start and end, and how do you traverse it, or how do you calculate the min cost? Which is really the toughest part of this, I think. So my logic here would be if you have a certain graph, right, and they're all connected, then you can traverse as much as you want in that island. Like you can go over all the connections that are possible within that. And really, because you're doing bitwise and, like traversing a connection can only reduce it because there could only be more zeros in the bitwise and of that connection, right? Like if there was somehow a connection that was 0 within this thing, then you do that cost and somehow magically your whole traversal is 0. So for any particular graph, whatever the bitwise and of that graph is, of all the connected stuff in that graph, then that's going to be the query answer for every single one. So actually that's pretty straightforward, I think. So after we do our graphs, right, we just need to do the bitwise and of the connections in the graph. So why don't we actually do that while we do the connection of the graphs? Actually, that makes a lot of sense. Instead of doing it separately. So when we have first the graph, or first an island, we'll just create a, I'll call this a bit and total bit for the island. And it should probably start off with whatever the value of this node is. So we take a node off this top. We seems a little redundant to do it here. I guess when we do the neighbor node, we can just do it here. Total bit is equal to the bitwise and of total bit and this neighbor node. I think the shorthand way of doing the and plus assignment would be total bit and equals bitwise and equals neighbor. I think that's the shorthand, but whatever. And then I guess we might as well update it. So after we do the island, so for each island, or whatever, no. So because the total bit is calculated, because the total bit is calculated and updated we need to have a updated value. So what I'm thinking here is, like, I could create a dictionary where the dictionary goes from the node to the total bit for the island, but then the total bit of the island can be updated later on. So if I were to just set a certain value to the dictionary for that node, then it might be an outdated value when you traverse more neighbor nodes. So you need something that is persistent after you calculate all this. So and what I think would be the simplest thing is for each island have a island number, and the island number can map to a set. The island number can map to a set of all the nodes on the island, and also the island number can map to the total bit for the island. So this is going to be a little bit of rearranging here. So it's going to be the island graph. So let's say, do I really need to change my other stuff? Is it going to be slightly more condensed? If you have a dictionary that maps the node to a reference of a set, that doesn't really shorthand or save memory if you have it to map to like a number, and that number maps to a set because you have the same space there. So I think maybe just I still need to keep track of the island number, right? So map the node to the island number. Let's keep track of what's going on here. So you have a node that maps to an island number, and the island number maps to, for each node you have an island number for that node, and then the island number maps to the set and total bit for it. Okay. That's fine. Okay, I'll have that. Let's say the island num, and this will be a dictionary. So we'll say the island number isle here is going to be starting with 0. So for each node, you do this stuff, and then after you do this stuff, you need to increase the isle number, just so I don't forget to do this. Okay, so you start with an island number, and then you start with the node, the island set, stack, the total bit is the node for that, and the island graph. I don't think I need this. I don't think I need that. So, or maybe island sets is going to be a dictionary, and island total bits total is going to be a dictionary as well. Alright, so we start with a set here. Actually, this set is just this set is the same thing as I'm going to store it here. Island sets for this isle is equal to this island. Okay, that's the connection there. and I need to update the total bit each time. Okay. So like after I do all this jazz, I'll do island total for this island. Isle number is equal to the total bit. And I think I don't think I need this anymore. The island graph. The island graph. I need to keep track of the island number though. So for each node, island number for this node is equal to this isle. Okay, so if we haven't seen a node, we're going to create a new island basically. If node not seen, create a new isle. Or island. So what does an island have? So an island has a set, has an island number, and a weight, a total weight too. So we say that this node has been seen, that this node is connected to this island number. And then for the set for this island, we start with that node, and to connect the island number to the sets associated with it, we just say isle set this isle number is the island. And then isle is basically is the island number, which is also the dictionary, whatever. Stack starts with the node, total bit starts with the node. For each thing that you see on stack, pop it. There's no more island graph. The graph is already connected to the set, so that's not necessary. And for each neighbor in the graph, the island adds the neighbor, stack appends the neighbor, you calculate the total bit, and then total bit is calculated for the island, and then you increase the island number by 1. Okay, and then let's go and just update this. So if the start is not in the island graph, so I think this is going to be the island number. Okay, so island number is maps node to isle, and this maps isle to the set of nodes within it, and this maps the isle to the total bit of costs. So here, using this stuff, if the start node is not within the island number dictionary, or the end node is not in the island number dictionary, then you pen -1. Otherwise, if the end is not in the, so they both have, so we can just compare island numbers actually at that point. So if the island number of the start does not equal the island number of the end, then that's also -1. Wait, if I have that, then why do I need to keep a set? I guess I don't need to keep the track of the set, do I? Or I don't need to store the sets. Yeah. I don't think I need to store the set. So if I don't store the set, I just need to keep track of the set while I'm doing the calculation, but I don't need to keep track of it past that. So I don't need to store it here. I'll clean up this code afterwards, but just making sure that this works. Island graph not defined. Okay. All right, that is not correct. Maybe I cooked a little too hard between testing. I'm gonna go ahead and print after the graph here. Print what my island numbers are. So 0 is island 0. Okay, they're all on separate islands, which is not correct. Oh, I see what I did. So each node you add it to the scene. Oh, yeah, I should be adding the neighbors to the scene. I'm not sure why I didn't do that. Scene.add this neighbor. Okay. Island number is just 0, zeros all around. Okay, so for each node in graph. Oh, no, that's still, you add the node to the things that you've seen. And then for each neighbor that you see, you add it to your scene as well. And then you go to the next node and you increase the isle. Actually that's correct. Okay, I'm gonna do another test case here. Because actually there is only one isle here, right? That's not unconnected. It's 4 is never doing this. So if I do a test case where there's, what is n? There's n vertices to the node. Okay, I see. I do a test case where I just say n is, there's 5 vertices, so it goes from 0 to 4. Let's say there's 6 vertices, and there's another edge between 4 and 5. Let's say it's node 4 to 5 with a cost of 1. So there should be 2 aisles. Okay. Okay. Yeah. It's supposed to be island number. Island number for this node is this isle. And I don't think I ever did it for this thing here. Island number for this neighbor is this isle. Okay, that's better. Okay, 0 is island 0. 1 node is island 0. 3 node is island 0. 2 nodes is island 0. Node 4 and 5 are island 1. Okay. And then here you have nodes 1, 0, 1, and 2, and they're all in the same island. Okay, that's correct. Okay, so back to the main point here. Actually, maybe I can do the total bit. Is that already done pretty much? So the total of walking on island 0 is 0 and island 1 is 4. That is not correct, I don't think. The total for island 0 should have been 1. Right, because it's walking. Yeah, it should have been 1. And the total for the other one should have been 1 as well. So what the heck did I store there? So I calculated the total bit. Total bit and neighbor cost, not neighbor. Still incorrect. Still incorrect. Total island total for this island is the total bit. So why is this still 0? Oh shucks, I'm so stupid. I started with the total bit being the node rather than the cost. Actually, if you start at this particular node, you actually don't have a cost to start with. So the total bit should start with the maximum. Does that make sense? The total bit starts with like all ones. Or I guess I could start with any neighbor, any neighboring cost. What's going to be easier? Having all ones. The problem with having all ones is if the total bit's -1, if I start with total bit as -1 and then I do an if statement, then I do an if statement every single time, which is kind of slow. I think maybe I'll start with all ones. So total bit is going to be, how do you make an all one bit? Sure. I want to make binary number of all ones in Python. What is it? Is this like 2 to the power 2 1? What is the maximum cost? Maximum cost here is they don't really say what the maximum cost is. I don't see it. UV, those are the nodes. Yeah, they don't say the maximum cost. Okay, I'm going to say 2 to the power 32 minus 1. Alright, let's try that. Okay, so traversing the first island is min cost is 1, the second island min cost is 1. Traversing this island min cost is 7. Is that correct? That is not correct. Should achieve the cost is 0. Oh, wait. So between 1 and 2, Between the cost of between nodes 1 and 2, how is this 0? So we need to achieve 0, we need to move the following edges. 1 to 2, wait 1, 2 to 1, wait 6. Didn't I already do that? For each neighbor. Oh, I see, I see. It's because I go from for each neighbor and neighbor cost. No, I really don't see. If you go from 1, the graph of 1 would have 2 tuples, 2 and 2, 6 and 2, 1. And you stack that onto, do you stack that onto the thing? So for each neighbor cost, you do the neighbor cost and oh, but you already said that it's in the island. So the second one you don't do, probably. So how to get around that? For each neighbor, if the neighbor is already in the island. So maybe you just need to, for each neighbor, you still need to take into account whether or not, so it could be redundant, but you do the total bit cost, the total bit and of that neighbor cost regardless, whether or not, and then you can kind of skip it. Yeah. I think this is correct. So 0, 1, that's still fine. Okay, yeah, the island, the total cost of the second island is, total cost of that island is 0. Okay. So for every query that is connected on an island, then the answer is going to just be appending the island total for that island. So the island would be, I can do island number at the start. All right. Okay. Sweet. And it didn't really do anything. I just didn't submit it correctly there. All right. I mean, that's a solution. All right, let's see if I can optimize this a bit. So memory usage and runtime is not great. Is there a faster way of doing the graph or a shorter way? So for every graph node, you have a list of the edges in the graph and the cost of that. I don't think this can be shorthand. So you need to have that graph. And then you have a scene set. Can you not need the scene set? I think you kind of need the scene set because as you traverse, you have like an island set, but then you have a global scene set. So I think you do need the scene set. And then you have 2 dictionaries, one for your island mapping, one from your node to your island number, and then from your island number to your cost. Okay, so I think maybe because the nodes are actually are actually labeled from 0 through n-1, I think you can use an array here. So the array is pretty much the same thing, but just using the index as the node itself. So we'll say the island numbers can be -1 for every island. So for every node, so it's times n nodes. and then man, the labeling here is just confusing, I think. Let's say node island map. Node island map. Okay. What was it before? Okay, let's change this to the replace function. Okay, yeah. Node island map. Replace all. Okay, so then you have the island number and island total, and that could also be an array. So this is going to be, I guess, probably just 0 times n. You don't need the set. And then you start with island number 1. And I'll just so I'll just change isle to island number. Island number. Alright, so island number starts with 0. For every node, add it to the scene. Okay. Create an island for it. The island map for this node is this island number. The island is going to be a new set. And then you have the island is going to be a new set. But we never store that set anymore, right? Do we keep track of it? If the neighbor is Ori in the island. No, yeah, we do need that set. Okay. The stack is the node. Total bit is 2 to 32 minus 1, so it's all ones. Pop the stack. Go through the neighbor. Calculate the total bit with the neighbor cost. And then keep on working the island if the neighbor is not already on the island. If the neighbor is already on the island, then ignore it. Scene adds the neighbor, island adds the neighbor. Okay. And then island adds the neighbor. Can I just use scene? Why do I need to have the island set? If the neighbor is in scene, then continue. Shouldn't that work? I think this works. If I just get rid of that set. If neighbor is in scene, continue. No, I guess I do something slightly off. So why doesn't this work? Neighbors in scene. Scene and island set. Scene and island set should do somewhat redundant things. Island. So yeah, this change definitely doesn't work. But why? Oh wait, maybe it's another change that didn't work. So I changed it to -1 as the mapping. Oh yeah, yeah. So everything is, so the query There is no node island map, is there? Oh, I see. Yeah, it's treating the array as a set now. If start, so if the node island map is of start is equal to -1, or the end is equal to -1, then append -1 is your answer. Otherwise, they need to be the same. Otherwise, yeah, I think that's the issue. Hopefully. Okay. Just double checking that that still works overall. All right. Okay, so I think here I just need scene. I don't think I need the island set. And then, so this gets rid of some sets. How is my memory compared to below average? Okay. But at least that gets rid of that. So if you've already seen the neighbor, then don't worry about it. And then, I mean, in theory, you can do like a Boolean array for this as well. So, scene is a Boolean array, false times n. I'm actually not sure how smaller or bigger arrays are versus sets. If scene of this node is true, then continue. Scene of this node is true now, and scene of this node is true now. Scene of this neighbor. Scene of this neighbor is true now. And if the neighbor is seen. Alright, just making sure that change works. Alright. Alright, how much increase or decrease in memory was that? Getting rid of this set. Okay. So that did change. I guess changing from a set from a array set to an array is smaller. Could I actually do an array here? So an array of array, 2D array. I don't think it's any faster though. 219, I guess there's a slight decrease. So if I do the graph is a 2D array. So if the graph is a 2D array that's empty, then I think it looks like this times n. I don't know if that works, to be honest. It's a list times n, where the list is tuples. I think that might work. Ooh. In which case I can't use node in graph. So this would be for every node in the length of n. Let's double check this. Let's print the graph at this point and return graph at V. And what does this give me? So bad at Python 2D arrays. Yeah, I don't think that. I think what if I did for, I don't know if this works, 4K in range of n. Does that give me enough? Okay. Yeah, I don't think I can do multiplication on empty lists. Because I think maybe they do concatenation. I'm not sure. So let's go ahead and do that quick check. Alright, so it's an array. Yes, 2D array. So the first subarray is, or the first entry array is going to be the neighbors of node 0, which is just this. And then the second one is the neighbors of node 1, the neighbors and their costs, node 2 and node 3. 0, 1, 2, 3, 4. What happened to node 5? Oh, node 5 is not here. 0, 1, 2, 3, 4, and 5. Okay, they're all there. Okay, so if I did that, then for each so it's not each node in graph, it's going to be each just node in the range of n. And then, okay, where do I use graph? For each neighbor and neighbor costs in the graph at k, where k is the current node value, that's still fine. I think that all works still. Okay. What is going on? How is my memory now worse than before by changing it from a dictionary to an array? What the fuck? How is that possible? Changing from dictionary to 2D array? I mean, I guess my speed is now fine. I guess accessing lookup in dictionary is slower than lookup or appending in dictionaries are slower than lookup or appending in arrays. Something is different in terms of speed, but I don't think the size should be different. Okay, well, okay, I don't know. This is just bizarre to me. Like, this is so much. 92 megabytes, 93 megabytes. So it's 91 megabytes, 92, so like 1 megabyte less. Alright, well, I think that's satisfactory. I'm gonna clean this up and then go over the summary. I think this is all fine to keep. This is a little maybe I can get the answer to be later on. All right, so we create the node. Okay, so every time you have a graph type problem, then you need to create a. Generally, I use default dictionary if I don't care, just for expediency, but 2D array is fine. 2D array to map start node to all its neighbor nodes tuple with node the neighbor and the cost. Well, you could also use default dictionary of this. Okay, so that's the graph portion, and then this is the portion for determine connected components, which are basically islands in the graph. And do calculations on it. Here we're going to track island number for each node and total bit for each island number. So you start with an island mapping, a node to island map, where it goes from node to island number, and then a total bit calculation for the island number. So and then you start with island number 0, and you start with having seen no nodes. So while you traverse each node, if you've already seen the node, then skip it. If node not seen, basically determine stuff for that island. So first, always really this set of code is always there. Like if you haven't seen something, then if you've already seen something, then just skip it, and then immediately afterwards say that you've seen it. It's always something that you want to do so that you don't forget to add the node to your scene set. And then after this, so the island map is the island number, stack has the node, and the stack does, I think this would be called depth first search, because breadth first search you use a double-ended queue, but depth first search of all neighbor nodes. And then total bit should be start with biggest possible, as each cost edge cost will reduce based on the doing a bitwise AND. When you do a bitwise AND with any two numbers, it's just going to be smaller because of the possibility of more zeros in the bits. And this basically is just the default highest value, and you're going to get lower and lower. So while there is something to stack, this is just traverse. This is just the depth first search. Pop the node off the stack for each neighbor of this node that we had in our graph. Reduce the total bit cost of traversing this island, and then and then change to when we say that we've already seen this neighbor. Technically, I think I could have maybe done this outside the while loop, like right here, but I think this is fine. I've seen it more often here. And then node island map this neighbor, and just record that this neighbor is now connected to this island number, and the stack needs to next. So the stack is just a bunch of nodes that we haven't processed yet for this island. After you're done with the island, then you store the island, the total bit for the island number, and then increment the island number. Okay. And then lastly is the answer portion, which is pretty straightforward. You have your answer array for each query that has a start and ending node. If the start and ending node is not connected, basically we never actually encountered it within the bunch of the graph only has stuff that was connected to something else. So if it's never registered an island number, then it's -1. So the query it's going to be impossible. If they're not the same starting ending values in the query, then it's not possible. Or starting the same ending island. And then lastly, if it is the same island, then the island cost is going to be the same. And I think that is it. All right, so in summary of algorithm, create graph to create graph 2D or create graph mapping so to go from any start node to its list of neighbors, and that's something you have to do for every graph type problem, because generally they don't give you something that straightforward to work with. They give you something that's more like edges, and you have to parse through the edges to create the graph. But and then determine the connected component, which is an island, using depth first search. Create, which is to say that you create stack that contains an initial start node, and add to stack more neighbors, and process everything in a loop, while loop. And the while loop is basically this thing right here. This is the key part. So the while loop is while there's anything in the stack, while there's stuff that you need to process, you take the top off, you process it, and generally just processing is looking at the neighbors, determining what you need to do with the neighbors, and in this case the cost of neighbors. And in this case is pretty much just doing this calculation, and then just some extra recording that you've done this. And then here kept track of island numbers for each node and total costs associated with each island number. And in different problems, there might be different ways that this needs to be calculated, but this one is pretty straightforward for that. All right, so that's the general summary. I mean, this is a hard question. It's hard to summarize everything. And then there's for queries. Use island number to determine if nodes are reachable or connected, and island cost for reachable queries. Right. And then time complexity. So if there's let's say there's n nodes, and which are the vertices, and say there's m edges, which are the connections. The time complexity to make the graph is O of m, because for every edge you need to create the graph based on it. So this is O of m right here. And then to create the island information, you go through each node, and for each node you basically go through each edge once. So you go through each node once, and you go through each edge once. So I think that's O of n plus m to make graph. To determine island stuff, this is O of n plus m. So overall, this is going to be O of n plus m. Okay, actually, there's the query aspect to it. So let's say the queries and Q queries. For the queries, you need to actually do queries. It's straight. It's just O of Q. So overall, it's going to be O plus m, O of n plus m plus Q. Yeah, it's not like you go over multiple times the same edge. Each time you see a neighbor, you kind of traverse to that neighbor, and you don't go backwards. So yeah. And then space complexity. What is the space complexity here? So the graph has a 2D array. So I think this is O of the size of the 2D array is the number of nodes. I think it's the number of edges, really. But then the default size of it is going to be the number of nodes. The number of lists is number of nodes. This one I'm kind of, I don't know. I think it might be O of n plus m as well. Ish. Yeah, you can have like n empty array, and then like, or n minus 1 empty array and one kind of big one. Yeah, I think it's roughly that. You definitely do need an answer array, where the answer array is for the graphs. For graph stuff. And O of Q. Actually, I'm not sure if you, when you do space complexity, you take into account the space required for your answer. I guess you probably don't. And answer takes a Q array. Like it doesn't make sense where you say that you require some space, and that space is how big your answer is. That's yeah. But, all right, cool beans. Oh wow, there's chat. Uh, um, sorry, I didn't see this chat. What if the answer for each query is the and in between always? I don't know when this I don't know when this stuff was actually said. So I will look at the chat